Okay, hi and welcome everyone to today's One World Mind seminar. Today's speaker is Filip Elvander. He obtained his PhD at Lund University in 2020. He then went for a postdoc in Leuven in Belgium before joining Aalto University in Helsinki in Finland in 2022. His research interests consists of many things. Among those are signal processing, inverse problem, and in particular methods related to optimal transport. And this will also be the theme of the talk today, optimal transport for inverse problems in signal processing and remote sensing. The floor is yours, Philip.
Yeah, thank you, Axel, and thank you for inviting me. So basically, it's as Axel says, this will be kind of the theme of the talk, and in a way, it's kind of a shameless sales pitch for using optimal transport in inverse problems, and in particular in signal processing applications, statistical signal processing, I should say. So my idea of this talk is basically to kind of give an overview of some signal processing problems where I think, at least, that optimal transport is a perfect fit for addressing some of the problems that typically cannot be handled by standard methods. So what we will talk about mostly is problems in spectral estimation, so both for, let's say, temporal signals, so frequency content, but also spatial spectral estimation, so things that have to do with target localization and so on. And basically everything will boil down to problem formulations where we have some type of inverse setting where the object of interest is a mass distribution, more or less. And then I will show basically how we can use optimal transport problems as regularizers for these problems and get really nice solutions and properties of the solution. And then I will just talk a bit about some practical ways of solving these problems as well. So this is based on joint work with a number of people. So Anton Björkman, who is my PhD student here, and then some colleagues from different places. So Isabel Hassler, who is at Uppsala University, Andreas Jakobsson at Lund University, and Johan Karlsson at KTH Royal Institute of Technology in Sweden. So, and yeah, here are some papers that the talk is mostly revolving around. So what is this then about? Well, basically the setting is fairly straightforward, I would say. So in a lot of signal processing applications, the type of measurement situation or data situation that we are in is basically something along this line. By the way, can you see my cursor? Also, okay, good. So the measurements that we have are basically some type of linear functionals of some mass distribution that we are interested in estimating. And, or we could also say that, yeah, we have some measurements that correspond to a linear operator operating on this mass distribution. So what could this be? Well, mu here is often the spectrum of wide sense stationary stochastic processes. So it could be, for example, electrocardiogram signals, sound signals, you name it. But it can also be more related to spatial distributions of power. So this could correspond to basically mass distributions over space corresponding to the backscatter that you would get from radar signals when measured on an array, for example. Similar things also happen in wireless communications. We look at the propagation channel and so on. So as an illustration, we could basically say that what we're interested in is estimating things on this form often. So here you see something where we have basically a temporal domain. So omega here is temporal frequency, so corresponding to standard oscillations of sine waves. And we also have another dimension that is more related to space. In this case, it's a field of view for an array. So basically saying from which angle of arrival do we have any incoming power. And typically this is what we're interested in estimating. So if we would get access to this object, we could say that, okay, we seem to have two targets at two different locations here, so corresponding to this angle and this angle, and then they have some different frequency characteristics that we could use, for example, to identify what type of target it is. So, a lot of problems revolve around this. And the main issue here is that the measurements that we have are typically nowhere near enough to actually estimate this thing. So, for example, we will not have that many measurements, and they will typically be quite noisy. So it's not so easy to just invert this relation straight away, say, for example, with least squares. So yeah, just maybe the most familiar setting when it comes to these things. So we have the Wiener-Khinchin theorem. So if we would have a relation like this, where RK would be the covariance sequence of a wide-sense stationary process, so something that we measure in time, then basically those covariance measurements correspond to Fourier coefficients of this underlying spectrum. So mu here is called the power spectrum of this signal. And in some cases, if we don't have any point masses and so on, we would replace this with the density in that case. So typically, when we have this relation, we for sure cannot measure it for all integers k. We will have a very limited set of measurements, and they will typically not be of very high quality either. So in order to estimate mu from R here, we would typically need to impose some other type of structure as well. So for example, if you think of a signal that would look something like this, so we have a periodic waveform, then if we can impose the assumption that it should have a Fourier series, and if we could also limit the number of harmonics in it, then we have made the problem considerably easier because we have imposed so much structure to the problem, right? But the problem is often that we don't really know exactly what structure we have, or we can have some type of idea of the structure, but it might not be exact. So an example here, in many situations, for example, when it comes to vibrating objects with some type of stiffness, the signal that you measure from them will not have this perfectly harmonic structure as we see here, but there will be some type of deviations from it. So here I've just plotted periodogram estimates of two different sound signals where this exact difference actually shows up. So the blue curve here corresponds to a saxophone. This is just a tube, so here basically the vibrations that you get are perfectly periodic. And as you see, you actually get something where you only have, or ideally, only have support on integer multiples of some fundamental frequency. But if we instead look at the vibrating string, it's not as simple anymore. So here we have a piano signal, so basically corresponding to very stiff steel strings vibrating. And here you actually see that you get deviations. And these deviations from perfectly, basically harmonic relations, they become bigger and bigger the higher the harmonic order becomes. So even though it would be easy, in some sense, to estimate the frequency content of the saxophone signal, because we can impose such a rigid structure to it, what should we do with the piano signal? Here we cannot say that it's harmonic, but it's almost harmonic, right, in some way. So the question here is, could we in some way use that? So we know approximately what type of structure it is, but we also know that it will not be perfect. But can we still exploit it in some way? And basically the problem here, if you think of maybe, let's say, standard methods to address this, is that basically the pattern and the deviation from the pattern actually lies in the support of the distribution. So it's not an additive error. We have actually basically shifted the support here. So not so easy to deal with necessarily. Similar things show up in spatial spectral estimation. So yeah, maybe some of you are familiar with this, but say, for example, that you have a bunch of sensors, so in what is called an array, and then they measure some incoming wave field. Then basically, if we start to look at the covariance between these different sensors, it's of course related to whatever stochastic process is generating the signals, but the exact structure is also related to the geometry of the array. So basically the time delay between different sensors. And just as we have here, we can express the measurements again with a simple linear equation. So the covariance between two different sensors here, so K and L, can simply be described as a linear function of what is called the spatial spectrum. So basically, how is power distributed over angle of arrival in this case? And this functional G is then typically determined by the geometry of the array. So how are sensors located with respect to each other, carrier frequencies, propagation settings, and so on. Typically, those can be more or less known in practice, or they can at least be estimated. So here, basically, trying to estimate mu here is the same problem as trying to find where targets are, for example. So here you can kind of see that the object of interest is not necessarily mu itself, but only where are the support points of mu. That's the critical thing, right? And as you can also imagine, as soon as something moves, the support of mu changes as well, right? Okay, so all good and well. But what happens then, let's say that if you would want to do tracking of some objects that move. So let's say that you have something like this. So here I've basically generated signals where you have two targets that move in angular space, and at different time instances, you record measurements from the array, basically noisy versions of this. And then you try to estimate the spectrum from those. And the problem here is that you have quite few measurements, it's noisy and so on. So if you just use the measurements in isolation, sure, you will probably get some type of peaks in the spectrum close to where the actual targets are. But you can also see that you get a lot of erroneous peaks. And in some cases here, you see that it's not necessarily even so that the two largest peaks correspond to the true targets, right? So here we could basically think of that if we assume that things move at some finite speed, this change in the support of the spectrum should be smooth in some sense, right? So with that in mind, shouldn't it be possible to basically exploit all the measurements when trying to track these targets? And again, the problem here is that this corresponds to change in support. How do we deal with that? And in particular, how do we deal with that when we don't know how many targets we have, basically when trying to do this in a non-parametric fashion, right? Just another motivation where it's a bit similar. So basically, if we think of this problem, it's a problem of trying to fuse information, in this case between different time instances. But we could also think of basically trying to fuse information from different sources of measurements. So think of an example like this. So here I've plotted out two different arrays. So the crosses here and the circles denote locations from different sensors corresponding to two different arrays. They both observe the same scene, and then if you think about it, it should then basically be possible to use both sets of measurements to estimate where we have sources of power, right? But again, there might be problems here as well. So one thing that's very typical is that you have what is called calibration errors. So for example, you might know quite well where sensors within an array are located relative to each other. But if you have two different arrays, it's not necessarily the case that you know how they are situated relative to one another. So here is an example of that. So basically, this array has been rotated slightly relative to what you assume. And as it turns out, it will not be possible to find a spectrum that will actually fit both of these measurements in a nice way. If you simply try to do it with least squares or something like that, this is basically what you get. So as you see, there should be two targets at the green pluses here, but instead we get 3 peaks of power here, and they are in the wrong location. Again, it's this problem with basically difference in measurements corresponding to differences in support, and how do we then deal with that in some nice way. So basically what all this boils down to is that we are, at least in signal processing, very used to kind of dealing with deviations that have to do with, let's say, the y-axis, right? We are used to thinking of additive errors. And that's very, very good in many situations, but as we've had in the examples here, it's not always applicable, right? So basically, if we think about it like this, if we have an additive error, fine, use some standard method. But if there's deviations in the support, we might have immediate breakdown of methods. And this is just an illustration here of basically what it could look like if we look at two, let's say, fairly standard distance measures for in this case, densities. So here I've basically plotted one density in blue, and then I've started to shift it relative to itself, and then basically compare it to itself using, in this case, just the L2 distance and the Kullback-Leibler divergence. And as you see, as soon as we start to move out, the distance basically, it grows very rapidly. And what is maybe even worse is that it saturates also. So if we have started to move, basically, so that we don't have any overlap of the support anymore, we get no information whatsoever about how close or distant the two distributions are. So for example, if we would have shifted it enough, and then let's say that we have some iterative method for trying to basically fit a spectrum to the data, if we're out here, we have no information at all, basically. Right, so problem in practice, and then what I will talk about basically in the rest of this seminar is trying to sell to you the idea of using optimal mass transport in order to deal with these problems, and basically arguing that it's perfectly constructed for dealing with this type of issues. So just briefly, what is optimal mass transport? It's an old subject dating from the early 1800s, and basically the problem is this. Let's say that you have two distributions, mu1 and mu2, over some space x. And then the question is basically, what would be the cheapest or easiest way of rearranging or morphing the first distribution as to be identical to the other one, basically? And the way that you measure this type of cost of rearrangement is via something that's called the ground cost, often denoted C, which is a function going from the product space, x with itself, to real numbers, positive real numbers. Typically, you would want this to be, for example, lower semi-continuous or something like that. Simple example, let's say that the space is some subset of R3, then we could, for example, look at the squared Euclidean distance to basically say that the further you move something, the more expensive it is, right? And the way that this was first formulated then by Gaspard-Monge was something along these lines. So you would basically want to find a mapping on this space that would rearrange the first distribution to the other. So T dash here is the push forward measure. And you would want to find such a mapping such that you would minimize this cost functional. So basically saying, how much does it cost to move from some location X to the image of X times how much mass you happen to have there. So this was then investigated in the basically the times of the French Revolution. Turns out that it's a very difficult problem to solve, right? Very difficult constraints, and basically the object of interest here, the mapping that we look for, shows up in a quite nonlinear way, typically. And there are other problems as well. It's not necessarily the case that there exist solutions here. For example, if you think of singular mass distributions and so on. So then what happened in the then 20th century was basically relaxing this to, instead of looking for a mapping T, we instead just look for a coupling M between these two spaces. So basically it makes everything a lot easier, because then everything that was quite nasty turns out to be linear, right? So basically If you have this coupling and then you integrate it along one direction, you should arrive at your first distribution, integrate along the other direction, second distribution. So linear constraints here in terms of this coupling, and the objective functional is linear as well, right? Because here you simply need to multiply whatever mass you move from some point x1 to x2 with, oh, sorry, typo here, should say x1, x2, there also. So nice thing here is that, yeah, it's linear convex, right? So that's very nice. And here there are no restrictions whatsoever when it comes to mass splitting. So there's no problem of taking, for example, Dirac point masses and splitting them up into several locations, right? So this is basically what we will then work with in the rest of the talk. So why is this nice? Well, basically we can get a lot of nice properties from this. For example, let's say that we have solved this problem and have gotten access to this coupling or transport plan M. Then basically you can use that in order to, for example, define interpolants on this space, because basically what this will give you is an exact correspondence from what mass goes where, and then we can interpret this cost function or ground cost function C as determining with what type of dynamic they move between these two points. And we will see an example of how you can design that according to your liking. But basically it allows you to construct things like these. So this is the same distributions that we had in the previous picture. So here's the start distribution, end distribution, solving this transport problem with, in this case, squared cost. This is what is called the displacement interpolant that you will get. So that's very nice. It means that we can actually try to infer intermediate distributions. So if you think about it, perfect in a tracking problem, for example, because here we can actually impose any type of smoothness that we would want to have. What can you do more? So you can also do averaging with this by, for example, saying that you use the minimal objective here as basically a distance measure or a cost. And with that, you can basically, let's say, define something that would be like a generalized mean or barycenter. So let's say that we have two distributions like this. So here we have something in blue and something in red. If we would just look at the Euclidean barycenter, it's not necessarily very interesting, right? It will just be averaging the two and adding them up. So not very nice. Whereas it gets a bit more interesting here in the optimal transport case, because here the barycenter will actually correspond to a displacement of the mass. So again, you can also think that, okay, that actually makes it very interesting when we have these problems where we have some type of, what would you say, oh, now I'm missing the word, but no, inconsistency between two different mass distributions. This would basically allow you to find some type of middle ground by actually having the ability of changing the support. Whereas looking at this thing, you cannot do anything about the support. All right. So what can you then do with this? Well, so first of all, I would just want to say that one thing that people have looked a lot at the last couple of years is basically extending this bi-marginal problem to basically allowing for couplings between more than two mass distributions. Definition is fairly straightforward. Instead of having two marginals, you would have capital T of those. And instead of looking for a coupling between two, you look for a joint coupling of them. So cost functional generalizes directly, and then marginal constraints, not very strange either. Basically, you would want this coupling to integrate out or marginalize into the different observed distributions, right? So looks very general, and it is, because basically you can model a lot of different problems by basically selecting this cost function, C, in different ways. So for example, you can do, or basically interpret this as tracking if you want, if you select C to have kind of a sequential decoupling form. So if we think of these different marginals as being observations at different time instances, And if we then let C decouple into basically pairwise, or kind of a chain-like sequence here, then this cost function will model exactly that. It will model basically what is the cheapest way of moving from this point to this point, then from this point to this point, and so on. So just comes in how you design the cost. Barycenter, you can do the same thing. So here you would typically add an extra margin here that you don't have any constraints on or not any observations of. And then you would link that margin to all your different observations. So basically get a hub and spokes graph of this thing. So, and then you can think of basically any combination of the two and different varieties of this. Okay, so how is this related
Sorry, can I ask a question?
Yeah, of course.
Let's going back to the previous slide. Here you introduce multi-marginal extension. And then you talk about sequential tracking. I think you have in mind like that these observations, observations are obtained at different time intervals. Is that right?
Yeah, exactly.
Yeah. So I was wondering, like, is it necessary to like model this problem in terms of a multi-marginal optimal transport problem, or is it also possible to, I'm just wondering, is it equivalent to like, let's say like between any two time intervals, it's just a regular optimal transport problem. It's just that the unknowns are now the distributions in between.
Yeah, I agree with you.
I'm not sure.
No, you can do that as well. Exactly. So basically what you're saying is that you would take, let's say, problems like this and then you would chain them together.
Yeah.
No, exactly. That you can do as well.
Okay.
So basically the reason of maybe doing it like this, that it turns out that you get, and yeah, sorry for not be or I will not elaborate so much on it in this talk, but it turns out that when you solve this in practice, then it actually turns out that this actually gives you a bit nicer behavior of the solution. Because, and we will come a bit to that. So basically when trying to solve this in practice, we will need to do some relaxations that will cause a bit of, let's say, spread of the distributions that we look for. And turns out that they actually get more concentrated if we have this formulation as opposed to basically what you were saying with this chaining together.
Okay. I'll wait for you.
But like in an idealist case, then it's exactly the same. I would say that if you have this formulation, you could add, let's say, sugar on the top as well. You could then start to impose more conditions in a very easy way also, if you want. But yeah, I agree. I mean, you could definitely do it with the pairwise formulation also. Yeah, good question. Same thing for the barycenter also, that we could see this as basically having a lot of pairwise transport problems. All right, okay, but so coming back to the signal processing setting. So basically, what we will do now is that we will take these transport problems and, I mean, more or less just superimpose them on these inverse settings, right? So in contrast to what we have here, where we actually observe our margins, what we would have in signal processing applications would basically be indirect mesh and noisy measurements of this guy. So we would instead have something like this. So we would have some linear operator operating on each margin here. So this would then correspond to our measurements, noise-free measurements, and these are then our observations. So then basically we need to here allow for some type of deviation that is due to pure randomness. So for simplicity, we could just quantify this by a least square error in this case. But you can do something more fancy if you want, and if you have more knowledge of, let's say, the statistical distribution of this guy. But so this would be maybe the simplest case. All right. So basically what we can do now, if we have something like this, is that we can take our measurements into account, however they may look, and then basically impose structure by this type of problem. So basically by choosing this cost function C in different ways, or I will just mention briefly a bit later, other types of additional constraints that we can put here. We can basically very much design or let's say impose prior knowledge that we have. So for example, we could say something about how smooth we expect, let's say, a sequence of distributions to be. We can do averaging of measurements using this formulation. We could also think of if we have some type of prior idea of what the spectrum might look like, we can also incorporate it in this formulation here, right? Then, of course, in practice, this is not what we solve, right? So typically we would actually take this problem and then we would do some type of discretization of it. So we'll talk a bit about that. So basically what we take here and what we've done in some papers is, straight off. You take everything and you turn it into matrices and, or tensors, I should say, in this case, and sums, basically. So what you have here is basically, just discretization of the different terms. So this would correspond to the transport functional here, and same thing here also. So G here would be some type of discretization of the linear operator. So it could be a matrix, for example, or if you have some other fancier way of implementing it. But something finite dimensional at least. So, and this comes a bit back to your question about like why not do it with some type of pairwise construction. And the reason basically comes here. So in order to try to solve this in some type of efficient way, so this would be a quadratic program if we just look at it, and it's a huge number of variables. So this is definitely not feasible to work with at all. It would be a bit better with the pairwise thing, but it could still be quite large. But what you can do then is that you can basically add a bit of regularization to this problem as well. So this is, I think this was proposed, when is it like 10 years ago, a bit more, by Marco Couturi. So basically add a term like this, D of M, where this is a type of entropy regularization. So basically something that would force some kind of spread of the distribution. So this will for sure be, doing some type of violence to this thing, but it turns out that it's, at least theoretically, not too bad. You can show that as epsilon tends to 0, the solution of this will actually tend to a solution of the original problem, a solution with maximum entropy for that. So it's not that bad in that sense. The reason that you do this is basically that it allows for a very nice dual formulation. So here, if we look at it, the dimension is ridiculous. It's huge. You don't need to have very fancy problems to basically have more optimization variables than atoms in the universe, basically. So not so nice to have on a computer. But the dual formulation is quite simple. So it actually looks like this. So this is the Lagrange dual of this problem. And basically here, as you can imagine, the optimization variables will then correspond to, basically to the different constraints here. So here we get something that's quite simple. Dimension is considerably smaller. And this is something that can actually be addressed in a nice way. So that we have described in the papers from a few years ago, basically how you can then try to solve these types of problems efficiently. Turns out that you can do this basically via, let's say, a block coordinate descent, so fixing all variables lambda here except one block, basically, maximizing with respect to that one, and then cycle through. Turns out that you get linear convergence when you do that. So that's quite nice. And the iterations themselves are not too bad either. So when addressing this, basically the iterations look something on this form. So you would start at some initial point, and then basically all you need to do is that you need to compute the projections of basically the transport plan that we have here, or current estimate of it. You project that down onto the different marginals, and then maybe the not as pretty thing is that you need to solve a nonlinear equation. So that's basically what it boils down. So very simple iterations. And turns out that even though this might look more nasty or so, this is not the big issue here. Basically, the bottleneck of the iterations is computing these projections. So what we have done in one paper, and then basically our sister group at KTH and now Chalmers and Uppsala have looked at basically exploiting different structures in the cost function in order to compute this in an efficient way. So even though we have a problem that is, I mean, pretty massive, due to that there's so much, often at least, structure in the cost function, the practical computations are not that bad because you can exploit so much patterns in it, basically. So this is pretty much it. Running this algorithm will solve this problem. And then for those of you who are, I mean, maybe more familiar or working with these problems in practice, maybe you recognize that this is very similar to the Sinkhorn iterations because it's basically same thing. So, and it turns out that if we would have maybe, let's say, the standard case where you would observe the marginals directly, so your operator here would just be the identity, and if you would have no noise in your measurements, so basically we would, let's say, model it here by letting this regularization parameter tend to infinity, the iterations boil down to just this, and this is exactly the Sinkhorn iteration. So it's definitely not strange in that way. So there's a direct link. So exactly as for the Sinkhorn iterations, we suffer from the same problem in terms of numerical stability. So as I mentioned here, we need to introduce this entropy regularization in order to arrive at this efficient scheme. And then ideally we would want to put this regularization parameter epsilon to be quite a small number. But I mean, okay, there are two things with that affects convergence speed, but it also basically messes up numerical stability of the iteration. So when epsilon becomes small enough, you will get overflow or underflow when doing this. In the Sinkhorn case, so basically in this case, there's a remedy to this. You can basically rewrite all these computations and basically allow avoiding having to compute exponentials. That's the big issue. So in the Sinkhorn case, you can basically put epsilon more or less as small as you want. We haven't figured out a corresponding way to do it in our case. This is not a problem, but this equation is. So if someone wants to work on that, I am very, very happy to look at the results after. So basically, we are inherently limited there in how small that we can put epsilon. And that then comes back to your question with this chaining thing. Turns out that with this formulation, we don't get as much of, let's say, detrimental effect from this regularization terms as we would get in the chaining problem. So basically, we get distributions that are less spread out if we use this type of formulation as opposed to a pairwise formulation, which then becomes important in our case because basically we cannot afford putting epsilon as small as we would ideally want, basically. Right.
I have another question.
Yeah.
Yeah, so in this case here, the tensor M here, it's of dimension, I think, n to the power of tau, right?
Yeah.
Is it possible to store this?
Definitely not.
So you can get you can do all these computations without having to store the tensors, is
Yes,
that?
exactly. Yeah, that's the key, basically. So you never need to actually compute this.
Okay.
So this comes back to basically having smart ways of computing these projections. Turns out
I
that
see.
you don't need to actually construct this object here in order to compute the projection.
Interesting. Okay, that's okay.
But it's as you say. I mean, for small problems, yes, then you could construct this. But as soon as it gets interesting, you cannot do it anymore.
Yeah. Okay.
But with that being said, you can still actually use a lot of the, let's say, fun stuff that we would want to have if we would have access to this. And we will see it in just a bit that you can actually, even though it's not possible to actually construct this M, you can still use it for interpolation, actually.
Okay.
So we'll see an example of that.
Thanks.
Right. Okay. Okay. So just coming back, what happens then if we solve these problems? So this was this array setting that we had from before, where basically there's a inconsistency between the measurements, or let's say there's an unknown error in the array measurement functionals. So if we then take this type of problem and formulate it, let's say, like this, where we let this ground cost function be this barycenter setup. So basically say that, okay, the cost between, let's say, this unknown margin that we're looking for, the barycenter margin, that the cost is simply the sum of the cost to the first margin and to the second margin, where in this case we just take the Euclidean distance. Then we can actually average the two measurements. And the result is something like this. So as you see, in contrast to this, we actually get only two targets, so that's nice, and they are just slightly perturbed. So of course we cannot expect them to be on the crosses, right? Because the data doesn't contain that type of information, but there's not a breakdown, right? There's just a slight shift of it. So that's quite nice. And then what you can do in this tracking case is that you can be a bit more fancy if you want when it comes to the cost function or ground cost function. So here, basically, we're only interested in quantifying displacement, right? So the further something moves, the more expensive it is. And in kind of a static case, that makes a lot of sense, right? Like the further you move, the more different it should be. But if we think about something that has movement, that's not necessarily a good physical explanation for it. So if we think about movement, then displacement is maybe not the problem, but acceleration, because we will have inertia in some systems. So if you think of that you have a heavy object and it's moving along some trajectory, it's not necessarily a problem that it continues along that trajectory, but rather deviations are problematic. And you can incorporate this quite easily, again, in a transport formulation by basically selecting this ground cost as the solution to optimal control problems. So let's say, for example, that if we take this setting and then we would say that let's introduce a hidden state in this case. So we have the angular position. So this is something that would actually manifest in the array measurements. And then we also have the object velocity here. Then we can write up just a simple model for how the dynamics work by basically writing it on this linear state space equation or state space form. And then basically say that, okay, the cost of moving between two different states, so pairs of angular position and velocity, corresponds to how much you need to basically accelerate in some direction, right? And specifically, the cost corresponds to the energy of that acceleration signal, right? So we can use that, and then we can construct this sequential cost function again. And then, as it turns out, you get something that works quite well. And it allows you to actually estimate the target velocity at the same time. So that we cannot see from the measurements, right? But with this type of formulation, you can actually, infer it as well. And on top of that, it also allows you to construct really nice interpolants also. So basically the different dots here corresponds to the times where we actually have measurements. We don't have any measurements from it in any intermediate times. But if we solve this problem, we can again use the transport plan that we got and these assumed dynamics in order to actually reconstruct target trajectories. So in particular, if you think about it also, this allows, in this case, trajectories that cross each other. This wouldn't be possible if we would have just a standard transport formulation, because in this case, this target would definitely start to move up here instead, right? Because it's displacement that's problematic, not acceleration in that case. Okay, just very brief words on something that has to do not with these array settings, but coming back to what I said in the beginning of these inharmonic signals. Basically, you can do kind of similar things there as well. So basically quantifying how close a certain spectrum is to being harmonic, so corresponding to a Fourier series. Not very strange. You basically look at how far do you need to move each, let's say, point mass as to lie on the perfect integer grid, basically, or integer multiple grid of the fundamental. So that you can formulate, and then what you can basically do is that you can construct a regularization function on this form, let's say. So here you again have something that measures transport. So basically, how much do you need to move stuff around in the spectrum? In this case, we only have one, or there are not two margins that we can actually observe, right? We only have, or ideally, even if we cannot observe it, the only thing that exists is this underlying spectrum of the temporal signal, right? Which we would here call mu. So basically, the constraints that we have here is that we would want to project the transport plan to that margin, and then we instead add assumption on the other margin that we have no measurements of whatsoever. So basically a sparsity thing here in this case. So what does it mean if you use this as a regularization function? Basically, it means that you would want to take whatever spectrum you have, and you would want to cluster it into as few Fourier series as you can, basically. So this mixed norm here will model exactly that. So the more that you spread out the transport plan, meaning how many Fourier series you need in order to explain the data, the more costly it will be. And then this parameter here will try to strike a balance between how much you need to move stuff and how many of these structures that you use. And then ideally, if you solve a problem like this, you would want to find a solution of this form. So here we would have basically two Fourier series that are superimposed, and you would want to decouple them into basically two let's say, harmonic series objects in this case. And you can use this again in this inverse setting formulation. So this is something that my student Anton has been working a lot on and recently presented at ICASP. And what you can basically get from this is that you get estimators that are very robust to these type of inharmonic deviations, whereas a lot of other estimators would, as soon as the deviation is too big, basically it breaks, simply breaks. But here you will get some kind of more, nice, slow breakdown, let's say. All right. I think that was basically mostly just quick thing that you can, again, just to kind of say how modular this thing. It's not a problem at all for, adding group sparse penalties kind of in this vein in order to have, let's say, broadband multi-time spatial spectral estimation. That's definitely feasible to do within this framework because it's so modular that you can basically just build things on top if you are careful enough.
首先，这个 L0 模型是离散的，其次呢，这三个模型都是
Maybe
NP
that's
的。
not us. So basically, just an example here. So here we have two different stochastic sources. So they send out some type of stochastic signal, and then you measure them over time, and they move. And what you can do is basically say that, okay, you assume that there are only few targets. You don't know that it's two, but you assume that there's not, ridiculously many. So basically, if you look at, let's say, the temporal spectrum, so just the spatial aspect, there should be support in only limited sets, right? Whereas you can't really say that about the temporal case because you don't know anything about the frequency content. But you can basically fuse these ideas together in order to be able to track these two guys from array measurements. And then, as you can see here, it means that you can actually achieve higher resolution than you would get with, let's say, standard group sparse settings. So in this case, for example, it's We have used also a type of, let's say, group lasso formulation. And even though you see that the estimates are quite good, when the objects become too close to each other, you cannot resolve them anymore. Whereas here you actually can because you're actually using all the measurements, right, in this thing. Whereas this can only use them time by time because there's not any natural way of incorporating changes in support in this case. Works on real data as well, so that's nice also. Right. Well, so okay, long sales pitch, but I hope that I've convinced you that this is a really nice tool to use in these type of inverse settings. And what I really want to convey is that I think it's so promising and so powerful that I think that there's more people should work on this. A few are, but to me it seems that basically the bulk of the work that is done in this field is in this case where you have directly observable margins, which is of course like very much the case in imaging and so on. But I think that there are so many interesting applications where we could use these tools that are, very powerful and promising. So I encourage everyone to get into this because there's so much freedom in designing these things. So you can basically work on whatever problem you find interesting or fun in this case. So just saying something about like what are maybe limitations or challenges. So basically, I mean, even though these tools that I talked briefly about allow you to address, I mean, quite big settings or so, that it's still feasible to solve them. It's still the case that, I mean, the higher the dimension of the problem becomes, I mean, eventually it's not feasible to do this anymore. So we need to basically figure something else out. There is work being done on this in what is called support-free optimal transport, for example. So there's some really promising things there. But anyway, more things need to be done for sure. And another thing that I think that is very interesting, and especially when it comes to signal processing applications, is trying to extend these concepts to non-positive objects. So here I've just talked about mass distribution, so something that's kind of inherently non-negative. But in many cases, the objects of interest are not necessarily that. They might have a sign, or they may even be complex valued. But they might still have this type of interesting geometrical properties that we would want to exploit. So we are doing some work on that currently in my group, on basically in the context of system identification. I had hoped that I would be able to talk about it today, but yeah, not enough time. But anyway, thank you so much for listening, and I'm happy to answer questions if there are any.
Yes, thank you, Filip, for the nice talk. Are there questions from the audience? Then maybe I can start with one. So you mentioned briefly that by playing with the cost function, you can impose different smoothness and structures on the solutions. Can you delve a bit more into that?
So yeah, for example, so if we think of, I mean, yeah, in this case, you get, so if you use this type of solutions to optimal control problems, then I mean you can get solutions that look on this form, whereas just simple or standard pairwise things would give you something that, I mean, if you think about it, it will be piecewise linear, basically. But this is just one way of doing it. One other way of doing it is, of course, to have something a bit more. Let's see, I mean, instead of having something like this, you could have a more complex graph on this. So, for example, I think maybe last year Axel Ring gave a talk also, basically using different graph structures in this cost in order to do fast computation. And as long as you kind of stay within that framework, you're still guaranteed to be able to do computations very, very efficiently. So I would say here, for example, I mean, you could for example, think of having let's say, higher order differences, also to have another way of introducing smoothness instead of using these control problems. That would be one way. You could think of using combinations of different things. So I don't have any slides on it here, but one thing that we've looked at is basically combining these barycenter ideas and tracking to get a bit more complex cost function, but then basically allows you to, at the same time, track and average measurements from different sources. So I would say that there's, and I should also say that the thing is that, at least if we think of the let's say basic mathematical properties of the problem, you can basically pick this more or less as you like, right? You still preserve convexity, and so if you look at the infinite dimensional case, of course you might run into nasty problems, but as soon as you discretize, nothing strange can happen. So the thing that you might lose is basically the ability to compute it fast.
Okay, more questions from the audience? Okay, then if not, let's thank Filip again for this nice talk. And yeah, see you next time.
Yeah, thank you for having me.